Okay, good morning everybody. We have to do this one as part of our relay training. The relay training will be later on uploaded to the Elmo, and we have to do everything over there as part of our learning curve. So big part of relay testing is you have to understand the switchboard, single line, drawing, and GA. GA means general arrangement. Okay, so don't hesitate to ask, and it's better to have a very good discussion among the group because everybody has a different background. Some of you are experienced, some of you came from a different skill set, breaker, cable, but we have to, because every day we're dealing with switchboard. So it's better to understand what is really a switchboard. Anyway. Okay, so I need to. So general arrangement, if you look at this one, this is the switchboard general arrangement when I was in my previous company. So all of these are blank, we have a spreadsheet and the client will provide us a specification of the switchboard. And you can see we have to fill out the requirements, like for example, the earth switch, all the at the bottom of the spreadsheet you can see the specs as well of the CT and everything. So all are blank, but this is the specs of the switchboard. It's not really clear, but later on you can see that specification of the specific switchboards. So this one is I believe this is GE, the one that we commissioned and handled it before, maybe around 2012. So this is the main enclosure. Inside you have the single line diagram, and you see that one there. It shows the joint of the bus bar, joint per panel is compartment design. You see the CT over here, CT, earth switch, and also this the outgoing cable, and this is the bus tie. Now, so initially from the design, the client will provide this, and we will provide the specs of the CT, the specs of the breaker, BT, and also if this is metering VT or metering CT or protection CT. We call this bus riser. It's a bit blurry, but anyway, let's go to second page. So I zoom it up. So general arrangement and single line. So if you zoom it up, you have a type of a different model or supplier of the switchboard have its own presentation or how they can present the one. So you have the rated kV of 24, service voltage of 22, power frequency, impulse voltage. If you look at that one as part of a testing group, the 65 kV will consider as your power frequency test voltage, or we call that high pot. That's from the IEC standard. So if you have this rated voltage, the test voltage is 65 kV for that one. And the second one, which you see impulse voltage, is a factory testing to test the endurance of or the specs of this board in terms of lightning strike. So that's your lightning strike, which is half wave of the voltage. We have one cycle. Where is the drawing, Nick? Anyway, we have half cycle. So when you have half cycle, it's only 10 milliseconds. One cycle is 20. So one cycle, that one is for your high pot. At 1 minute, the board should survive. That's some kind of torture test for the switchboard. But in the factory, before they deliver this on site, they have to do some lightning test, or they call this impulse test at half wave. So one cycle is 20 milliseconds, and this impulse test is half wave or 10 milliseconds, but it's way too high compared to the normal testing that we do here on site. And you have the capacity of the bus bar and the main bus, how many fly. This is 1 times D10. It means just only one fly. If you want more capacity, you have to put them together, to make it thicker. And the control voltage, you can see that one there, the charging motor of the breaker. And what is this? Anybody can tell me about IP4X?
Ingress protection.
Ingress protection. It means sometimes you can see that in specs of your mobile, or if you buy some waterproof speaker, you know, it says ingress protection. There is in IEC standard, you can say that what is the meaning of 4, if this is a dust protection or any solid object protection. And the next one is for the water. That's why you put X, because this is not submersible. But if you can see in your speaker, sometimes if you buy some submersible speaker, IP65, IP67, it means that speaker can withstand under the rain, or if you drop it in a pool, you know, or even the iPhone that you have, it's IP67 or 65 something. So that is the specific specs of this. So when we go to the factory, in my previous job, we check all of this, you know, gasket, you know, make sure that it meets the IP4X. That is about the external construction of the board. It means that no foreign object that you can poke inside, it should be contained properly. Now this is your single line. This is your funnel 4, 5, 6, and so on. So I just zoom it from the first one, from the first slide. So the application, this is outgoing feeder for this specific panel. And also you have main switch, that's the spec of the main switch, which is the breaker, and the earth switch, and the capacitor voltage divider, which is, you see that thing that, some kind of, what you call this, blinking, when you energize the bus. That's the capacitor voltage divider located in the bushing. So you have the CT, and on the CT, you have the spec of the CT. You know, you have the model, and you have this 800:1 and 1600:1, which is, you can see 2 taps. You can choose which tap it is. And at the bottom, you have the specs of the CT. From this one, if you say 5P20, it's automatic, it's a common CT for the feeder. It means that it designed to measure current at a very high fault current. Like for example, if you have 800:1, so the primary is 800 times 20. So if you multiply at 20, you can go with KA or kiloamps, but still it's within 5% error. So that's the difference. And you have 10 BA burden. Burden means whatever connected to the CT, all the resistance, cable, test block, CT link, going to the coil of your relay, that is the burden. It means that the burden is the capacity of the CT to push the current. You know, if you see some kind of remote protection coming from transformer remotely going to the board, sometimes the VA is big because it considers the voltage drop to push the current, you know, without a drop. So, and also on the spreadsheet, because when I prepared this before during tendering is, of course, I have to look for a specific model as well that meet the protection. So I put the brand over there. Also the local and remote. This is remotely controlled by the SCADA as well. When we do the testing, so on the design, we allow for local function as well. Put it in local, and we can functionally test the controls and also the dimension. You know, schematic drawing, terminal diagrams, and the cut-out drawing. It means the cut-out of the cable entry. So I put some sample here later on. You can see on the table because I cannot display everything on the screen. So still the same. You have these specs over here. Normally, when the client on the design stage send us the requirements, it's all in wording like this. You know, what we're gonna do in my department is I have a what you call this, a drawing guy from AutoCAD to break down this in the control interpretation. Like for example, you know, on this one here, Key interlock system will be provided by the customer, so they're going to provide us the scheme of the interlocking. We have to interpret that in a control schematic. So push buttons are to be shrouded, which is, again, it will come up with the requirements of IP protection, ingress protection. That's internal. The one that we discussed earlier is the ingress protection externally for the enclosure. But inside as well, the client can say that I need a ingress protection for the terminal blocks. I don't want my finger to be touched that energized part. So you have to provide some shrouded. So they have to determine that one, and we have to comply. So each protection relay has a separate trip lockout flag, RMS. So you have the test block and also a flag down indicator. And short circuit withstand of 25 kA for 3 seconds. Very, very high. You know? Short circuit. It means that it will not explode, or it will not, dissipate in 3 seconds, having that sustained 25 kA short circuit. It's really big.
This is the mechanical protection.
Yeah, that's the construction of the board.
Yeah.
So all we're gonna do is we have to get some specs as well from the builder, GE, Gelpag, and Siemens, or whoever is the manufacturer of the board. That they have to comply with this with type test certificate. So there is a separate entity to blow up the board at 25 kA to contain the fault inside. No? So mechanical interlock, so door can only be open when BCB in test position or withdrawn. So you have that mechanical interlock plus back up by some kind of solenoid for electrical interlock. We have to put that together. So when you read the specs of the board, everything of this will be met by the schematic. That's why we're here. We have to understand that one. So you have electrical interlock only as well. So only when the bus bar edge switch is open, the bus tie and incomer BCB could be racked in service position. So there are some solenoid interlock that we need to allocate to prevent the movement of the ACB or BCB. Only when the bus tie and incomer and so on BCB is in this position and the bus earth can be closed. Because if the bus tie is closed and then your system is not designed to sync together, it will create short circuit. So all of this stuff, you have to convert this later onto the schematic. And that's the thing that the site acceptance test, the commissioning, make sure that all those specs is met by the drawing. So speaking of the ingress protection, this is from IEC 295. The left-hand side, the one that I mentioned earlier, is for the solid bodies. And the other one, you see IP4X, it means that it never designed to use outdoor because it put X there on the specs. So the builder of the panel will make sure that if you put IP4X, it means that protected against solid body larger than 1 mil tools or small wires. So that's how they design this one. There are some switchboard I know that is submersible, but we normally never do that here. Maybe some marine, some ship or whatever, But in our area of practice, we are on dry land, so that's fine. So if you go higher, it may be more it became dust protected as well. I haven't seen in some of the mindset specify 5 for dust. I don't know why. So yeah, if you go lower, like IP1, it says protected against solid bodies larger than 5 mil, accidental contact with the hand. So it means that if that one is specified, like for example, if IP1X was specified inside the board, it means that if you put your hands at the back of your hands, you touch it in the terminal, you cannot touch those energized parts like terminals because this is the requirements. So that's the ingress protection that we have. Now, if you look at this one, I think this project is 2012 from my previous company. So anyway, so ingress protection, if you look at this is the technical specification from a builder of the board, you know, when we went there in China to do some factory testing over there. So if you look at the height, we have to measure that, make sure that, you know, it met the requirement, because all of these height requirements was approved by the client. Consideration that how do you put this, or, you know, lift this and install this inside the switch room. If the switch room is concrete and the allowable entrance is this big, you should maintain that requirements that you have. When this approved dimension was approved by the client, you know, that's fine, you know, we can accommodate that on site. So you have to measure that. And also the bus bar is 1250 vertical and 1200 to 2500 vertical bus. And the weight as well. When talking about the weight, it's talking about one panel only. Because when we ship this panel from overseas going to Australia, it is on a crate individually, and we have to assemble it here one by one, including the wiring. And also the specs of the material, and here we go. Protection degree of panel is IP4X. That is external. When you go inside, all the wiring, IP2X. So he go 2X, so what does it mean? So protected against solid bodies larger than 12.5 mil. Example, finger or hands. So if you poke your finger there, there is a very less chance that you can touch the energized part. So that's what the requirements of the client. You have to follow that. Color and also the full front axis. So that's the spec. So if you look at this internal thing, when we do the wiring, we have to comply with it. You see those, even though we remove this cover, when you put your finger over there, still you cannot touch those terminal. Only you need the screwdriver to touch it to comply with the IP2X requirements. And also the IP4X, if you look at the external of the board, there's no way that you can poke any tools there, a specific size of screwdriver or little screwdriver, because there is no exposed terminal. Even the current injection was using test blocks. So you cannot see any opening there because it's IP4X and inside is IP2X. Any question? So if you look at this, even this one have a shroud. And the terminal of individual here, you cannot poke it with your finger. You know, I believe this is some signal externally, dry signal, dry contacts. So anyway, to carry on, if you look at this internal arc flash classification, why I'm sharing this one, because we are dealing with the switchboard every time we go to site. You know, we have to understand what is the switchboard. And all of this thing that installed in the switchboard, you have the VT, CT, the protection relay, and also when you are on site, you are dealing with sometimes energized board. In the other side, you're working on the front or at your back, energized, and you're working here. So we have to understand that environment. So if you look at the rated voltage again, 24, and the power frequency is 65. Rated lightning impulse is withstand is 125, which is, again, it's a factory testing about lightning strike, which is half wave, 10 milliseconds to withstand this lightning strike. So they're gonna test that in factory. I've seen how they do it on site, on the factory. So rated current, so that is the selection of the rated current. You know, if 630, you can see only one fly. Or 1250, 1600 amps, the bus bar will be put piggyback and put on top on each other, you know, to accommodate the one. Now we go here. As a relay tester, you have to understand this one. Relay short time withstand current at 3 seconds, 20 kA, 25 kA, and 31 kA. You know. So what do you reckon the changes they're gonna do there? And also, the rated peak current is 50 kA and 63 kA and 80 kA. That's the peak that it can withstand during short circuit. On switching, when you do switching at normal condition, so you have like, for example, current flowing at maybe 1,600 or 80% of that. But if there is a short bus bar or a short cable on site and you switch on a breaker feeding the feeder, your peak current will reach this. So it's 2.5. Normally on IEC, it's 2.5 of the rated KA. Let's check. You have any calculator? Like, for example, 25 times 2.5. Yeah, 62.5. So on IEC standard, the peak withstand current during fault, when you close the breaker and you bridge, for example, they bridge the load of the breaker, it can withstand, you know, the fault current at 63 kA, or as per IEC standard, it is 2.5 times the rated short circuit current of the board. And arc resistance test. So this specification need to pass for the type testing. They're gonna bring this in the laboratory and then, you know, simulate this fault in the board, and the board should withstand everything. And this one here, internal arc flash classification. Have you seen this in the nameplate? Anybody can see this in the nameplate on site? What does it mean? 11 kV, 12 kV, and the internal arc classification is AFLR 35 kA, AFLR 25 kA. Any thoughts about this?
Flash.
Yeah?
The voltage and flash.
Yeah, inside the cable box.
Yeah?
Some departments.
So it'll trip out. Yeah, it's
So it means that,
1 second.
yeah, it means that our previous client required that I want the board to be AFLR. It means that I want to reinforce my board to withstand the blast front, lateral and rear. Some of the switchboard you can see arc flash FL. It means that it's safe for you to stand in front and on side. If there is a blast, the weak spot is at the back or maybe on top.
Some are designed to blow towards back,
Yeah.
isn't it?
Yeah. So, but for this one, for the specific client that we have in 2012, he specified, the designer, we want to withstand, this board designed to withstand front, lateral, and rear.
So what's the A then? The letter A? What does
Arc
it stand
flash.
for? Oh, arc.
Yeah. So this is the internal arc flash classification. In the RMU, you can see this one as well. So sometimes, you know, if you know more about the specification, then you come across with, so this is the design. So you can see that AFLR or arc flash, internal arc flash classification is protected front, lateral, and rear. So they allow only the blast to, you know, exhaust on top. See this louver?
Arc shoots.
Arc shoots. So the compartment of the breaker, so if you're standing here, you know, it's all compartment is separately compartment for each. For the breaker, this is the door. So if there is an explosion in the breaker, this flap here will explode on top. You are still safe here in front. And also the busbar compartment is also a separate compartment. If there any explosion inside this compartment, the other compartment will not be affected because it's a metal-clad switchgear. So again, the explosion will go on top. And also in the cable zone, this is where you terminate your cable. If there's any explosion here and you're standing here when the cover is closed, you know, the explosion will go on top. That's why they allow this, you know, arc flash, what you call this, some kind of duct. And it will be blast outside the switch room. So you see this wall over here. And sometimes you have this arc flash study, you see this on site. You notice that one? Anyway, I'll go to it later on. So why we have an arc flash with standard, you know? Because this arc flash study lately has become a more popular to address the safety. There's a lot of people, you know, having some accident on site because of this. The board is not designed in an arc flash proof. You know, the older one, especially the older one, you have to very, maybe if you know this now, you have to look at how old is the board. If the board is too old, I don't think it was considered to be, able to withstand those blasts, So clear guidance on how to perform the arc flash testing. So this is how they do it on the type testing company. So GA, this is a specific brand from GE. So resists to mechanical and thermal stress when there is an explosion. Protect the operator against any risk resulting from devastating effect of possible internal arcing. So the cubicle design allows for arcing to be contained, internal suppression, mechanical, and that's the requirements. And when we blast that in the laboratory, they're gonna inspect again if there is some kind of melted metal and everything. So this is a compartment A, B, C, D. So it should be able to withstand that. Now, so this is the GA testing of the model. So you see the blast is all exhaust on site. So they're gonna blast this, explode this on site, the specific short circuit to comply and to certify that the specs that you put on the nameplate is really, certified pass. They're gonna monitor everything. And if you look at this on site, they put some kind of arc plus level to 4.6 kA. So sometimes I'm just thinking of, really, did you really read the nameplate? That's fine because that's the site policy. We cannot bend that one, even though we know when we read the nameplate of the board that it has an arc plus classification, internal arc plus classification, 25 kA. And those people, they're wearing bomb suits and everything at available fault is only 4.1 kA. I mean, there's nothing, But still, site policy need to be followed, We have to respect that one. And this is only for awareness, safety awareness of people who work on front, because sometimes we work in the front or besides the switchboard, which is energized, and the other one is isolated. So that is, you can see the breaker, the CT, and the cable zone. That's the side view of it. And the bus bar interconnection from one panel to another panel. And that is inside. It's really designed properly to handle the specific blast. This is normally we connect here for our ductor test. That's the shutter, mechanical interlock of the switch and the board. This is the earth switch. So we allow sometimes motorized operation, remotely controlled by, it depends on the requirements of the client anyway, remotely controlled by the SCADA. So any question? Because sometimes we see this on site and we need to understand what is internally. This is the CT, the busbar type CT as well. And this is the potential indicator, the one that I'm telling you, which will be covered as well in our schematic. This is your mimic bus, and this is your control circuit cable entry at the bottom for inter-panel interlock. And this is your space heater. Why do you need space heater? Yes.
So it doesn't create nitric acid.
Yeah. So you have to maintain that specific temperature inside and to avoid accumulate moisture. So space heater, pulse indicator, and so on. This is a capacitive sensor at the bushing of the main bus. And that's how you see it. The mimic bus, everything again is as per the design and the schematic as we go through. Ordinary panel, and you have this VT panel. What else? So I think you're familiar with this anyway. CT, earth switch, breaker, we wrapped it out. So you see it's called METALCLAD because its compartment is separated from each other. Even you close the door properly and you work here on this control circuit to do some testing or visual checking, still you're safe. Basically as per the specs of the board, you're still safe even there's some blast inside. But because of the requirement of the arc plus requirement inside, we have to follow that one. Yeah. So that's a different panel configuration. Metering panel is only VT and incoming. So inside of the main physical board, it will be later on come down to the single line. So this is where we look at it when we do the testing. Hope I can what you call this? I can zoom it on. So I'm gonna go with specific drawing. I think that one is here. Yeah. So what you can notice here. So you have the double-ended drawing. So you notice that on the single line, this is just to give you some overview of the single line. If you see on the drawing that there's a thick drawing like this, it means that it's a power cable or a bus bar. And if you go thinner line like this, it means that it's a control cable feed to the relay. And again, this is the ANSI code of the protection. So you have 27 under voltage. So any question about this? So 10 BA plus 0.025. So there is again, you know, what is the difference of this? This is very important as well. This one
Conductor.
and this one.
Breaker.
So you can see that X is designed to break the fault. But this one is fuse. The fuse will be the one who will open the fault. This contact is not fast enough to break the fault. So that's why there is a fuse. So that's part of reading the drawing as well. When you do the testing, and you can see now that he uses this 5P20. This is a typical CT specs that they use for the feeder. Yeah. So the class is what do you call this? Some kind of accuracy testing, accuracy of the CT. 5P20, 5P20. That's a typical specs for the overcurrent. Any question before we go to the next slide? Okay, I see. It's